This week in lab we are going to be looking at both the SN1 and SN2 reactions. Let's review just a moment. Let's look at review leaving group ability. For both the SN1 and the SN2, the iodide is the best leaving group, so our alkyl iodides are the most reactive. These are going to be more reactive than an alkyl bromide, since the bromide is our leaving group. Alkyl bromides are more reactive than alkyl chlorides. Chloride anion has the leaving group, and these are much more reactive than the fluorides. Fluoride has the leaving group. So our best leaving group is the iodide. Now, the reactions that we're going to be looking at this week in lab, we're using alkyl bromides, so it's a bromo group as our leaving group, and the alkyl chlorides. So we're going to be focusing on those two. So this same order applies for both SN1 and SN2. Let's talk about the SN2 reaction. I'm going to go generic here for our reaction, for our mechanism. We've got a lot of reactions that we're doing this week. We're doing 24 reactions. So I don't expect you to write the mechanism for every single one of them. You can just do the generic mechanism here. So for our SN2, we're starting with some alkyl halide. We're going to be reacting with sodium iodide. It's the iodide that is our nucleophile. There's a full negative charge on the iodide, full plus charge on the sodium. It's the iodide that is our nucleophile. Now, this reaction is not supposed to work. Remember I said we're doing bromides and chlorides, alkyl bromides, alkyl chlorides. Because the iodide is a better leaving group, so they should not be able to replace a chloride or a bromide. Now we play a trick with it. I talked about this in lecture. We're going to do the reaction in acetone. And that is important, that it's in acetone. The mechanism for the reaction, our nucleophile, our iodide, will attack the carbon that has our leaving group and kick off the leaving group. And we have substituted the iodide on. Now, what got kicked off is an X minus. Sodium would balance the charge out there. Whether this is sodium bromide or sodium chloride, these are not soluble in acetone. And so they precipitate out. So the reaction cannot reverse, because the bromide could be a nucleophile. Iodide's a better leaving group, so it could come in and attack, kick the iodide off, and go back the other direction. But it can't go back the other direction because both the sodium bromide and sodium chloride, whichever one happens to come out, these are insoluble, they precipitate out, and that prevents the reverse reaction. Sodium iodide is soluble in acetone. So it dissolves and the reaction can take place. Those precipitate out, reverse cannot take place. So this is a trick that we play on this reaction by doing the reaction in acetone. We're forcing it to go to the right there as it's drawn. Let's talk about the SN1. And again, I'm going to go generic. Now we're using silver nitrate in this reaction, and we're doing the reaction in ethanol. Ethanol is going to serve as the solvent and also as the nucleophile. Now, this one here, we're also playing a little trick on this one. We're going to make some things do SN1 that doesn't want to do SN1. So the chart that I gave you in lecture as far as which way a reaction is going to go, it's not going to apply here. We're going to make some things, some reagents do an SN1, some alkyl halides do SN1 that don't really want to do SN1. The silver nitrate, silver loves halogens. A silver cation, this is an ionic bond. The nitrate doesn't matter. Let's just take the nitrate off. It's that silver cation. That silver cation is a Lewis acid. And our halogen atom, this is a Lewis base. So I'm going to show you a different mechanism than what we discussed in lecture, because I didn't discuss using silver. If you recall in lecture, we just had to wait for SN1, we just had to wait for the halogen to leave off all by itself. We're going to use the silver to help it leave. So the halogen atom is going to give a pair of electrons, donate a pair of electrons to our Lewis acid, or Lewis acid accepts that pair of electrons. There's now a plus charge on the halogen atom. Follow your arrows. Initial tail becomes more positive by charge. Final head becomes more negative by charge, so the silver is now neutral. Now that halogen atom does not like having a plus charge. It's an electronegative atom. If anything, it would like a negative charge. It does not want that plus charge. What we've accomplished is we have made the halogen atom a better leaving group. This is now a really good leaving group. That halogen wants to leave because it doesn't want to have that plus charge. We went from an okay leaving group to a really, really good leaving group. So we take electrons out of the carbon-halogen bond. Those are going to go onto the halogen to get rid of that plus charge. That gives us a carbocation. And we get a silver halide here as a byproduct. This will precipitate out. And that's how we know the reaction is working. We'll see those precipitants come out. Let's go ahead and finish the reaction. So our nucleophile will now add to the carbocation. Ethanol adds. more step to become neutral. We'll take more ethanol to act as a base to pull off the extra proton. And we've made our product. But what you're going to be observing, we're looking for the precipitant, because we can see that. Same thing with the SN2, we had the precipitant. So the sodium chloride or sodium bromide was precipitating out, and we're going to be looking for that precipitant as well. That's something we can see. So we can see if the reaction is working. Now, you're going to be doing 12 SN2 reactions and 12 SN1 reactions. Let's talk about these. So there's 3 groups of compounds in your procedure. Let's first look at each of these. You're going to do each one of these as an SN2 reaction. SN2 conditions. So we're using the sodium iodide. And let's think about what we have here. If you analyze these, we have a primary alkyl halide versus a secondary alkyl halide versus a tertiary alkyl halide versus a phenyl halide. Now, if you recall, for SN2, we talked about in the lecture, methyl halides react the fastest, then primary, then secondary. Tertiary does not do SN2. Phenyl halides and vanillic halides do not do SN2. So, for SN2 reaction with these, what you should observe is that the primary alkyl halide will go first. The secondary alkyl halide will go second. You should not see a reaction for the tertiary. And you should not see a reaction for the phenyl halide as well. Now, in your procedure, it says if a reaction doesn't occur within 5 minutes, if you don't see any precipitant within 5 minutes, it says to put your tube in the sand bath, and that will help speed things up. The primary should go right off the bat, no problem. You may have to heat the secondary, and even if you heat the tertiary and phenyl, they shouldn't go, but if we put enough heat to them, we might get a little bit of reaction. Very, very small amount. We're also going to do SN1 with these same compounds. So let's think about SN1. SN1, you're going through a carbocation. And so for the SN1, we talked about that the tertiary alkyl halides react first, followed by secondary, followed by primary. Phenyl halides do not react. And that's because of the stability of the carbocation. Before I write those up, let's just review stability of carbocations. A tertiary carbocation is very, very stable. We said that was more stable than a secondary carbocation. We said secondary is more stable than a primary carbocation. and primary is more stable, or about a little bit more stable than a phenylhalide, phenylcation, or a vanillic cation. And those are more stable than a methyl cation. Methyl cations do not exist. Now I left some space here. What I didn't talk about in lecture, I'm going to go ahead and put it in here because we do have some examples of that here, is if the cation has resonance, we know resonance stabilizes a molecule. So if we have a carbocation that can do resonance, say with a double bond, then that's going to provide it some more stability. Well, how much more stability does that provide? The resonance basically bumps you up one spot. If you have a primary carbocation, for example this one, a primary carbocation with resonance, then it's going to be about the same stability, pretty close, I'll put approximately the same here, as a secondary with no resonance. Those are going to be about the same. So the resonance basically bumps you up one spot. Primary with resonance is going to be about the same stability as a secondary without resonance. If we have a secondary with resonance, it's going to be about the same stability as a tertiary with no resonance. Again, the resonance basically bumps you up one spot. And of course, if we had a tertiary with resonance, I'm out of room here. I'll just write tertiary with resonance. Then that would be the most stable. So the resonance bumps you up one spot. Later in some of these other groups, we have some that has resonance. These do not. But let's go ahead and look at these. So, based off our cation stability, that's going to lead to which ones are going to react first. For these, our tertiary, for SN1, the tertiary should react first, followed by the secondary. That should go second. And the primary, if you can get it to go, it will be third. It may not react. It's down here on this end, not very reactive for SN1. And the phenyl halide should not react. Okay, so there's our order that we should see for SN1. If you can, you may or may not see a reaction here. It will have to go with heat if you do see anything. And the primary, it may have to go with heat as well. But that should be the order there. Let's look at group 2 compounds. And we'll analyze these as well here. See kind of what we should expect. I'm not going to tell you everything on these. I told you everything on this group 1. I'm going to leave a little bit for you to discover on your own in the lab. Let's look at group 2 compounds. Let's classify our alkyl halides. You see they're all chlorides, so they all have the same leaving group. There's no difference in leaving group ability. First one here, this is a primary alkyl halide. This one is a primary alkyl halide. This one's a tertiary alkyl halide, and we have another primary alkyl halide. Let's first talk about SN2. Okay, for an SN2, methyl halides are the fastest, then primary, then secondary. Tertiary does not want to do an SN2. So we should not have a reaction here for the tertiary. Again, put enough heat to it, we might get something happening with it. It's not doing SN2, but it might do some elimination or something, make it go. But it doesn't want to react at all. Now the other three are all primary. Remember with SN2, the reason the methyl halide reacts the fastest is because it's got less sterics around it. It's completely open, that carbon is completely open to get backside attack. SN2 is all about backside attack. So there's no sterics for a methyl halide. Now we don't have a methyl halide. We have primary, but again we're looking at sterics. SN2 does not like any sterics. That's why the tertiary doesn't react. Nucleophile can't get in there and do backside attack on that tertiary to kick the halide off. But looking at our other three, they're all primary, but there's a little bit of difference in the sterics. Let's draw some hydrogens out here. I'm going to go ahead and put the hydrogens on here so we can kind of see how much sterics there might be. Trying to get in here to do backside attack. If you examine those, since I've drawn out all the hydrogens, let's say my eraser is the nucleophile. This one here, because of that double bond, that puts less hydrogens there. So it's a little bit more open to come in here and do backside attack. You look, there's a little bit more room on this one to come in and do backside attack and kick the chlorine off. This one here is not too bad. It can get in here to that carbon, but it's not as open as our 3-chloro-1-propene. This one here has got a little bit more sterics. If it tries to come in behind, it's got some other methyl groups out here that's kind of help blocking a little bit. So that's going to slow that one down. So what I would suspect for these, for SN2, less sterics. They're all three primary, but less sterics on this one. I would think this one should go first. This one's got less sterics than that one down there, so this one should go second. And finally, this one third. And again, tertiary should not react for an SN2. So SN2 is all about the sterics. Let's look at SN1. SN1 is all about carbocation stability. Tertiary of these, tertiary should go first because it's a more stable, for SN1, more stable carbocation. The other three are all primary, but this one here has the double bond. So once the halogen leaves, then the carbocation that you have has resonance. So this is going to be a primary carbocation with resonance. And again, that resonance bumps you up one spot. So this is, as far as SN1 goes, this is going to react very similar to a secondary alkyl halide. So I would think that this one is going to go second. And the other two might be pretty close to the same. If I had to take a guess, you're talking about, you want groups around it, you want protection, you want sterics to protect the cation. This has got more stuff around it. I would think this one will be third, and this one here will be fourth as far as SN1 goes. Let's look at our last group. Now, if you notice in our last group, we have different halogens. We have bromo groups and chloro groups. Bromo group is a better leaving group. We talked about that. It's a better leaving group than the chloro group. Let's look at SN2. Now, well, let's first classify our alkyl halides. We have a primary, secondary, primary, secondary. Now, for the SN2, methyl halides react the fastest, then primary, then secondary, and tertiary does not do SN2. So, primary should go first. We have primary with a bromo group as the leaving group. We got primary with a chloro as a leaving group. Bromo is a better leaving group than the chloro group. This should go first. Now, if you look at the others, I have secondary and a secondary. Bromo is a better leaving group. This should react before this one. This one should be the very, very last one to go. That one should be fourth. But I am not going to put up the other two. Now, why didn't I? Take a look at it. We've got a better leaving group. Bromo's a better leaving group than the chloro. So as far as leaving group goes, this one should react before that one. But as far as our classification, primary should react before secondary. So what's more important? The leaving group or the sterics? This one got less sterics than the secondary, but bromo is a better leaving group than chloro. So you will determine that order which one is what's more important, leaving group ability or the sterics for the SN2. Let's take a look at SN1. For SN1, we're looking at the stability of the carbocation. So tertiary reacts before secondary, and secondary reacts before primary because we get to more stable carbocations. So of these up here, secondary should react before a primary. And if we look again, bromo and chloro, bromo is a better leaving group. This is going to be first for an SN1. Got the best leaving group, and we have the most stable carbocation. Secondary is the best we can do here. Now, if we look at the other two, primary, bromo is a better leaving group than the chloro. So the worst one of the bunch for an SN1 reaction is the primary chloro. This is fourth. We know that. Now, the other two I'm going to put question marks beside. We have bromo that's a better leaving group than the chloro, but if the chloro leaves, you get a secondary carbocation. If the bromo leaves, you get a primary carbocation. Secondary is more stable. So what's more important? The leaving group ability or that carbocation stability? So I'll leave that as question marks to let you determine that in the lab. Now, these are two totally separate reactions. So maybe with one of them, don't think it has to be the same on both. Maybe one of them, it's the leaving group ability, and maybe on the other one, it's all about the sterics. So don't think you have to get the same thing on both. They could definitely be different. One may be more important on one of those. Now, let's take a look at our procedure. So with our procedure, we are looking for precipitants. That is indicating that the reaction is taking place here. You're looking for a precipitant. Now, the precipitant can be a solid in the bottom of the test tube or reaction tube, or the solution may just become really, really cloudy. That's just really fine precipitant that's kind of floating around in the solution there, but it's still a precipitant. So if it gets really cloudy, that's still showing that a reaction is taking place. So with both the SN2 and the SN1, we're looking for that precipitant or cloudiness. So for the SN1, it's the silver halide that's precipitating out. For the SN2, it's either the sodium chloride or sodium bromide that was precipitating out. Now, this is very important. Before you do the SN2 reactions, remember we're playing the trick with acetone. So go ahead and wash your test tubes or reaction tubes. Wash those just as you normally would. You can use the detergent and then wash with deionized water, but the last thing that you want to do is wash them with acetone, and then don't do anything else. Last thing, wash them with acetone, because all of our reactions are done in acetone as a solvent. So if you wash them with acetone last, that's going to take out anything that might cause us problems. We'll dissolve out any impurities or anything in there, contaminants that might cause us a problem. Now, I don't like the way the procedure, I need to change this, the way it's written up. It says to add all this stuff and record times it takes for precipitants to form and everything. But if you're just timing these, it's like, is it starting to precipitate or is it not? Do I start timing now? Do I stop my timing now? I don't know. Is that precipitate? It's difficult if you're timing each one. You don't know when to stop your timing. You know when to start it because it's when you put everything in there. But when do I stop it? So the best thing to do is to do one group of these. So you're going to do 4 compounds, a group like, for example, group 1. And we'll do SN2 on group 1. Oh, I got SN1 stuff here, but same thing. We'll do SN1, we'll do 4 at a time. You're going to put in, it says 100 milligrams or 100 microliters of each compound in each test tube, 1 in each. All of our compounds this week are liquids, so you're going to have 100 microliters in each one. That's 0.1 milliliters. So put 0.1 milliliters in each. Now you may want to label your tubes. You can use some of the blue painter's tape and label them A, B, C, D, or 1, 2, 3, or whatever, so you can remember which one is which. You want to know, like for group 1, which one is the 1-bromobutane and which one's the 2-bromobutane, and so on and so forth. So you may want to label those. So you've got 0.1 milliliters in each of these. Of the 4 compounds, we got 1 compound in each tube. And then you're going to be adding our solution. You're adding the silver nitrate in ethanol for the SN1. We're doing the sodium iodide in acetone for SN2. Okay, so set up for your SN2 or your SN1. We'll talk about SN. I only brought 1 bottle in here, so I didn't bring a SN2 bottle. So I'll turn it around this way so you can't see the label. We'll pretend that's a SN2 bottle. That's the sodium iodide. You've got 0.1 mils in each. I want you to be as fast as possible from this point on. When you're adding our reagent into our reaction tubes, you can be as slow as you want putting the 0.1 in each of the different compounds. But when you go to add either the silver nitrate or the sodium iodide, I want you to be fast. We're adding 1 milliliter of each And these syringes are 1 milliliter, and the 1 mil is almost to the top. Now, you pull all the way to the top, it would probably be about 1.1 mils if you went all the way to the top. That's okay, as long as it's the same in each. So what I would suggest, so that you can really watch as far as which one goes first, which one goes second, is to be very fast about this. Just take the syringe, pull it to the top, and squirt it in, and get it into each one as quickly as possible. So just pull it. Whoop. Trying to set everything up here where you can see it on the camera, and I knocked it off. So pull it up, squirt it in, pull it up, squirt it in quickly as possible. Pull it up, squirt it in, pull it up, squirt it in. So that was pretty fast, and then you can watch. You got them all in there about the same amount of time. There's a few seconds difference, but you can watch and see which ones start to show up precipitant first. Now, so you're doing group 1, group 2, group 3 for SN2. You'll do each of those 3 groups for SN1. Now, if you notice on the SN1, for your reaction tubes, again, you will want to wash them out. You can use the detergent and deionized water and everything, wash them out. You can even wash them with some acetone if you want. But the last thing for SN1, before you're ready to do your reaction, rinse them out with ethanol. There are squirt bottles. We put squirt bottles out with ethanol in it. The last thing, wash your tube with ethanol before you do the SN1. Ethanol is going to be your nucleophile. We don't want any problems. That will take out anything that could potentially cause us a problem. So again, last thing you do when you're washing, wash with the ethanol before you do the SN1. For the SN2, last thing, wash with acetone last before you do the SN2. Please pay attention to that. SN2, wash with acetone last. SN1, you're doing SN1, wash your test tubes with ethanol last. And don't wash with anything else. So you're going to do the same thing as we just did, as I poorly demonstrated there. Try not to spill it like I did. 0.1 mils in each reaction tube of the 4 compounds you're doing, whichever group you're doing. So if you're doing group 1, you got 0.1 mil of 1-bromobutane in that one. You got 0.1 mil of 2-bromobutane in the second one, and so on and so forth. You got each compound in a separate test tube. And you're going to do the exact same thing as I just, again, poorly demonstrated. With the silver nitrate, pull it up, squirt it in, pull it up, squirt it in. Just pull the syringe all the way to the top, pull it all the way up, squirt it in. Try to get it as quickly as possible into each tube so you can watch which ones react first. So I don't want times as far as, you know, watching the clock and recording a time. You do need to keep track of time a little bit, because it says if you don't see a precipitant after about 5 minutes, place it in your sand bath, and your sand bath should be on a setting of about 0.5 to 0.75, and leave them in there for about 5 minutes and see if anything happens. There may not be anything that happens, but some of these will, they just react slower, and so they will eventually form a precipitant with some heat that will help them react a little bit better. Okay, so again, with all of these, you're just looking at the order. I don't care about the time. Which one goes first? Which one goes second? Which one goes third? Which one goes fourth? When you're finished with these reactions, all of your waste will go in the halogenated organic waste this week. You can see everything we've got's got halogens on it, so everything needs to go in the halogenated waste this week. So, in your conclusions, I want you to address some things. some points. You are going to compare the nature of the leaving group, bromo versus the chloro, and this last group is good for that comparison. So you're doing that both for SN2 and SN1. Look at, talk about comparing the structural effects of or alkyl halides. So primary versus secondary versus tertiary versus the phenyl versus the allylic. The allylic is the one that I drew there that had the resonance. That's an allylic. And then also talk about the effect of temperature on the reaction. Did you have to put heat to it to get it to react? Because if you did, that means it's not very reactive. So talk about all that in your conclusions. So this lab should help you learn a little bit more about SN1 and SN2 reactions.